4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Good morning, good afternoon, good evening. I'm Ian Table, or better known as Mintynet. I'm here today to present my talk titled Value Pasta Auto, How I Built It and Saved $28,000. First things first, who am I? You could say I'm the ultimate car hacker. I built this kit car 17 years ago now. It's a Tiger Supercat. It's based on the Ford Focus 2-litre engine with the Ford rear-wheel drive Sierra rain gear. It only has 3 ECUs, of which 2 of them I built myself. One of them is the Mega Squirt for the engine control, for spark and fuel. The other one is the one in the top left-hand corner there. It's a GPS data logger that talks over CAN bus to the Mega Squirt and saves the data for analysis later on. Life and the British weather gets in the way, so I don't get to drive it as much as I'd like to. But there we are. On to my car hacking credentials. You may know of me due to my building my car in a box PD0, which is most of the electronics from a 2014 Peugeot 208. I built that at the end of 2018 after seeing 3PO at DEF CON that year. It actually thinks it's a fully working car. I have previously presented for ASRG on how this was built and how I now run the car hacking village in the UK. I take my car in a box to events in the UK. It has once been to Amsterdam. Fun time through customs. Ask me about it if you ever meet. In 2020, there was meant to be a bit of a tour of Europe, going to besides Dublin, Brussels and Stuttgart. However, Brexit and COVID got in the way. Then the advantage of COVID was some of the conferences went virtual, so I did actually manage to get to present and use my hardware for global conferences I may not have gone to in person. I have actually been asked to take my car in a box to numerous conferences globally, including India, Australia, Philippines, Singapore, Brazil and USA. It is portable to a point, but I don't think I'd ever trust it going through an airport because it's a big box with lots of wires in a metal frame and it would probably not go down well with customs. So that's where a car in a case comes into it. So on to what is Pasta? Pasta was originally released by Toyota Info Technology Center at BlackHat Europe 2018. I have actually seen it in person in September of 2019, but I didn't actually get a chance to have a play with it. So what is it? PASTA stands for Portable Automotive Security Test Bed with Adaptability. PASTA is designed and developed with the following philosophy. It must be open. It must be based on non-proprietary technologies. Adaptable, usable. Users should be able to rewrite the firmware of the ECUs, redesign the architecture and connect their own devices, for example. It must be safe. There should be no real actuators. It can avoid incidents such as wheels, brakes and windows should be realized by a simulator rather than the real things. And finally, it must be portable. The platform is preferred to be small and portable so that users can study, research and hack it anywhere. So what does it actually look like? Well, here is a picture of Pasta in the real life. The case itself is about the same size as the average gentleman's case. Top half of the case has inputs and outputs. The bottom half of the case has the 4 ECUs. I'll go into that in a second. There is a link there that gives you some more details of the original Pasta GitHub repository. If you want more detail about it, I will only be skimming over some highlights. So that is where you should go. So what is Pasta? Pasta is an open source system, or so it says. That GitHub repository contains schematics, firmware, hardware and software design files, and CAN definitions. There are 4 different ECU classes: gateway, powertrain, body, and chassis ECU. The gateway ECU is the only one that actually uses all 4 CAN buses that can be on the ECUs. The other 3 only uses one. That 4th CAN bus on the gateway is for the OBD2 port in the bottom right hand corner. There is all details in the GitHub repository. However, there isn't much information on how the top half of the case interacts with the bottom half of the case and how the inputs and output work. Looking at the picture and reading Pasta 1.0 ECU hardware and software spec, you can actually find out it says that the I/O is connected via serial using SCI 0. Looking at all the CAN definitions, it basically shows that all of the CAN definitions, all the switches in the top half actually are initiated with a CAN message from the chassis ECU. So that is where they will be connected on mine. So what is Pasta? Pasta has what they call a white box ECU. That big black chip in the middle there is a Renesas RX63N processor. It has 2 megabytes of flash, 256K of RAM, real-time clock, Ethernet MAC, USB 2.0, 3 times CAN 2.0, I2C, SCI, SPI, and probably some other 3-letter acronyms I've missed out. The 4th CAN controller is actually provided by an MCP2515 by Microchip. And then in the middle there, you can see 4 identical sort of circuits shown. They are the 4 NXP TJA1050 CAN transceivers. They run up to 1 megabit per second. Top left-hand corner, the yellow connector is the RS232C. Below that is JTAG, and then just above it is the battery for the real-time clock. On the reverse of the PCB, there is a micro SD connector for future expansion. When I first started looking at Pasta in 2020, before I built it, the actual chip there was available. It was about $26 each. However, that chip is no longer available through most chip suppliers, mainly because of the shortages, and I don't think they actually make it anymore, because it's quite an old generation of Renesas chip. There is a slightly similar chip available through Mouser. However, it is $15, but there is a minimum order quantity of 480. So if you actually wanted to build this with their chip, that would be $7,200 on the processors before you even started. So more information in the repository is the CAN definition file. Here is an abstract of that CAN definition file. It shows the source and destination ECUs for the messages, the frequency of how often the message is being sent, and finally how the data is encoded within the data bytes of the CAN message. An example is the top row in red, brake operation indicator. That has a source of the chassis ECU. It is executed upon on the powertrain ECU. It has an ID of 26, which is 01A hex. It is sent every 10 milliseconds. Its data length is 2. Its off or minimum is 0. And its on or maximum is 1023. And its unit is percent. Just after the last column there is a little formula that says 256 times A plus B, all divided by 1023, gives you your percentage. There is quite a lot of different messages in here, going forward and backwards between the different ECUs. I will summarize them on the next page. As I said previously, there are 4 500 kilobits per second CAN buses, body, chassis, powertrain, and OBD2. Looking at this summary table, it shows that there are messages sent between ECUs at 10 millisecond timing, 50 millisecond timing, 100 millisecond timing, and 500 millisecond timing. The chassis ECU itself generates 810 messages per second, The powertrain ECU generates 668 messages per second, and the body ECU generates 380 messages per second. That gives us some total of 1,858 messages the gateway ECU has to cope with every second. It's actually double that because those messages then have to be sent out on the other side to the other bus that needs the communication. So that gateway ECU is doing 3,716 messages per second, which is quite a big number, really. The inputs and outputs for capacitor itself. There are 3 LCD screens, one for the powertrain ECU, one for the body ECU, and one for the chassis ECU. As you can see, they show the wheels, etc. on the powertrain, lights and windows on the body, and on the chassis it shows things like the rev counter and speed, fuel and temperature. There are switches in the top half of the case. They are all connected somehow through to the chassis ECU. There are 3 potentiometers for brake, accelerator and steering. There are 2 rotary encoders, including push, which are used for front wipers and washer, and also front lights, including flash function. There are 3 toggle switches: shift position, blinker or indicator if in England, or rear wash wiper. There are a total of 8 push switches. 4 are used for the windows up and down, and the final 4 also have indicators, which are the ignition, door lock, handbrake and hazard light. Not shown on this picture here is there is actually a USB Bluetooth adapter in the top left-hand corner, I believe, of the case. That is used for the connection between capacitor and a remote control car, which works over Bluetooth. So you can drive the remote control car from here by using the potentiometers for brake, accelerator and steering. So on to my version of the hardware. Value capacitor auto, because it's slightly cheaper. The software is written using the Arduino IDE. The first thing I had to do was work out whether the microcontroller and or the library would be able to send enough regular CAN messages for the number required on the 3 different ECUs. So the maximum so far is 810, but potentially there could be more. The library I was using for communication for the additional bus is the MCP2515 library. That is written by Corey J. Fowler, GitHub link shown. What I did was to write a script for one of my nano cans to send CAN messages, as many as they could, for 5 seconds, analyze them using a generic Saley logic analyzer, and then take an average over those 5 seconds. A single 8-byte CAN message takes about 240 microseconds on the wire at 500 kilobits per second. So there is a theoretical maximum of about 4,000 messages per second for a single 500K CAN bus. So on to my analysis of the different libraries. The original library used from 2016 would allow for 848 messages per second. If you can see there, looking at the library itself and the data sheet, this first instruction here is read a register to see whether the transmit buffer is free. The microcontroller then writes in the 8 bytes of data. After that, the microcontroller writes in the data length. Next command here is to write in the 4 bytes of header. It finally writes in a single bit to say transmit the message, and then after the message has been transmitted, it reads a register to confirm that message has been sent, and then it all starts again. As you can see on the graph here, there is fixed timing between this bit, and also this bit and this bit, and this bit and this bit, and finally this bit and this bit. That is a fixed delay of 250 microseconds within the SPI command that says do something, send the message, or do that part of the command. So what it was, that could be removed. On a later version of the library, in the 2017 September version, those delays were actually removed, and the library itself could run 2,606 messages per second. Again, it's using exactly the same method of sending the data. It checks a register to see whether the transmit buffer is free. It then writes 8 bytes of data, writes a single byte of length, 4 bytes of header, final byte here to say transmit the message. Then all these bytes here are a read to see whether the message has been sent. On this occasion, there are 13 reads. When it finally confirms it's been sent, it then finishes and then allows the device to send the next message. So the only problem is I still think it can be done a bit better. So reading up on the data sheet, I found another command that is in the data sheet of the MCP2515 that allows you to load the entire transmit buffer in one go using 13 bytes instead of doing it from 4 different commands, and then the final command to transmit. So I modified the library itself to do this function. It now was possible to get 3049 messages per second. I'll show you here. We assume that the transmit buffer is empty because we're the only ones sending messages. So we send the 17 bytes of data, I think it is. No, 13 bytes of data into the buffer. We then trigger a transmit here. We then poll it to see whether the actual message has been sent, this time 17 times. And finally, then we clear the interrupt that says that the message has been sent and everything can start again. The distance here, the time between the bit here of the data being loaded and the actual message being sent utilizes the Arduino digital write function to change the state of the chip select pin. That takes about 8 to 10 microseconds. So if we actually modify that to use direct port manipulation, we can again make it even faster. The final analysis came up with a library function that could actually send 3,309 messages per second. As you can see here, we write the 13 bytes of data and instantaneously it then writes the message to say send the message. We then poll it again 17 times, and finally we clear the bit that says that it's been successfully sent, and then everything starts again. The way that this is quicker is it uses direct port manipulation, so this only takes 2 microseconds as opposed to the 8 to 10 microseconds previously, using the Arduino digital write function. The next part of the puzzle is what microcontroller to use. Originally, the plan was to try and use an Atmega 2560, but it had a low CPU speed of 16 megahertz and a lack of internal CAN controllers. This is an issue because if you have 4 CAN controllers on a single SPI bus, you would potentially be forever waiting for the SPI commands to say either a CAN message has come in or a CAN message needs to go out. So that one was parked. I did have a look at the Adafruit Itsy Bitsy M4, which has an ATSAM D51 running at 120 megahertz. Problem with this one is, again, it doesn't have any internal CAN controllers. Some of the ATSAM D51 processors do, but not the one used by Adafruit. Finally, I found the Teensy 4. This has an advantage. It has 3 CAN controllers built in. It also is an ARM Cortex M7 running at 600 megahertz. It can be easily overclocked to a gigahertz if you add some heatsink to the processor. Those 3 CAN controllers, 2 of which are CAN 2.0, but 1 is CAN flexible data rate. It also has a large number of I/O, PWM, and analog channels. So that's why that one was chosen. Here is an output from some benchmark testing for microcontrollers. The Arduino Mega itself, or the 2560, has an core mark of 7. The Metro M4, which is a similar chip to the Itsy Bitsy M4, has a core mark of 215, which is about 30 times faster. But the Teensy 4 has a core mark benchmark score of 2,314, which technically means it's about 300 and something times faster than the Arduino Mega. So it should be okay and should be able to cope with the number of messages and things we're going to be sending. Next part of the puzzle was creating the PCB. Here is the PCB version 1.0. Bottom left-hand corner is the TNC4 here. Above that are the input and output connectors. It's an automotive grade connector. Next to that is a battery for the real-time clock. In the middle here is the CAN controller for the 4th CAN bus. All 4 actual ECUs have this, but the only one that's actually using more than one bus is the gateway. Just on the right here, the 4 separate circuits that all look the same are the CAN controller circuits. The third one down is slightly different because it's a CAN FD capable controller. Doesn't use it at the moment, but could potentially in the future. Again, this connector on the right hand side is for CAN and I/O, CAN and power even. There is a mistake on this one. If you can see right in the middle here, there is a footprint of a NeoPixel. However, I put it on the backwards, so it didn't work. So I had to replace it with a surface mount LED and resistor. It works okay. I did create a version 1.1 of the PCB, but I never actually had it fabricated. I then created a version 1.2 of the PCB. This has additional pins for the interrupts, both inbound and outbound, for the MCP2515 CAN controller. This has actually been swapped out in the gateway ECU because it uses all 4 CAN buses, which means that I can trigger messages either being sent or received via those interrupt pins faster than if it were to be using the SPI bus. So the other PCBs that are required is for the I/O in the top half of the case. The I/O function is provided by the MCP23017 I2C I/O expander, each of which has 16 I/Os, as you can see at the top. 16 pins, each can be used as inputs or outputs. There is a power rail here and a ground rail for connection to the different switches and things. It's 4 analog inputs, analog 0, 1, 2, 3. There is a serial port here for the next in displays, which is serial 5 on the TNC. This connector on the right here looks very similar to one on the ECU connector. However, it is keyed slightly differently, so you can't get the cable the wrong way around. This one is black, the one on the ECU is grey. Some of these connectors actually have dual use. The analog 2 and analog 3 are used by the powertrain ECU for serial 4 for the Bluetooth adapter, so we can remotely control the car. There are 2 additional I/O pins up the top here. They are used to set the ECU ID, depending on whether they're high or low, but that is done with cabling on the board once it's created. This is what that board looks like, populated and connected to the switches and things. It's a bit of a cabling mess, so I'm not going to pull it out and show you anything more than that, but it does actually work quite well. So value passed to autos, inputs and outputs. Again, we have 3 screens to the powertrain, body and chassis ECU. They're 3.5 inch in size. They are created by Nexion human machine interface screens. I'll show you a bit more about that in a second. Majority of the switches present are connected to the chassis ECU. Again, there are 3 potentiometers, accelerator, brake, steering. There's 2 rotary encoders for lights and front wiper. There's 5 toggle switches for gear, indicator, windows up, down, and rear wiper and wash. And then finally, there are 6 push switches. These are used for hazard, lock, unlock, horn. And then the final 2 push switches have indicators as well, which are for the ignition and the parking brake. There is 2 additional components in the bottom left-hand corner, which is another potentiometer and rotary encoder. They are connected to the powertrain ECU for mode selection purposes. So I can put it into Bluetooth mode, which allows for the control of the car, or you can select other modes to change different dials on the different ECUs. In the bottom left hand corner, you can actually see a Bluetooth BTO5 adapter. That again is connected to the powertrain ECU to send the data over to the Bluetooth car. So what does the actual value paster look like? Here is the case, closed up, all secure. It's 115 by 345 by 255 millimeters. Or for you in Imperial land, that's about 5 inches by 14 inches by 10 inches. Here's a picture of the case open. Again, you can see the 3 screens in the top, all the buttons, and then in the bottom half you've got the 4 ECUs. If you look there closely, you can tell that the front and rear of the ECUs are actually using PCBs for the end plates. That just allows me to get a decent cutout on the ends without having to do it with the aluminium on my kitchen table. In the front half of the box, or bottom, shall we say, there is the OBD2 port in the middle here. That has 2 CAN connections. 6 and 14 go back to the gateway ECU. 3 and 11 go to this flying bit of lead. That can be connected to 2 out of the 6 cables here. Those 6 cables are the 3 pairs of CAN buses from the other 3 ECUs. In there is a fuse holder. Behind the back of the fuse holder, those connections are actually connected together so that you can just jumper into 3 different ECUs. Here is again a close-up of the top half. Here is another close-up of the bottom half. The little blue box in the bottom right-hand corner is a power supply. You can feed in 12 volts, which will also feed 12 volts to the OBD2 socket. So if you've got a powered OBD2 adapter, it will actually work. Top half of the case looks like this if you accidentally open it and it falls out. Actually using spare PCBs to hold it all in place. If I take those away, you get to the back of the actual perspex in the top. You can see the rear of 3 different displays, the 2 different I/O boards for the chassis and powertrain, and all the different switch functions and things. So code, bit more information on that. As I said previously, I had to start with the repetitive sending of the messages with dummy data using timer-based interrupts for the different groups of messages. Once the I/O PCBs arrived, I had to write the code to interact with the inputs and the next-in displays. The next-in displays require data in both directions. You can make it do things, but it can also send information back to the MCU saying some state has changed. Originally, there was 4 separate ECU bits of code for the 4 different ECUs. However, I aggregated them into a single code base. Some of those original ECU bits of code is still in my GitHub repository. There is no warranty on it, but you can see how bad my coding is. So on to the next-gen human machine interface devices. These devices, you have to design the details on each of the screens that are there, including serial commands that need to be sent back and forward for the data. There is code required in both the ECU and the display itself. Here is a picture of the IDE for the next-gen displays. They're actually quite cheap. They range from like 2 inches all the way up to 11 inches. This is the body ECU. You can see all the different parts on the screen that may or may not be present. You can make them hidden or unhidden depending on what you need. There is initialization things in the bottom here, so that when it gets to that screen, it will initialize certain things and show certain things. But I will just show you, there is a simulator function that you can use. Here is the default part for this screen. Once it's done in the initialization, there's an instruction on the bottom left-hand corner here that says page 0. This will then turn the device to page 0. It actually then has a intro screen that it goes through, swaps onto page 1, and then swaps to this screen here. Once it has completed that screen, it will send this data here back to the microcontroller to say, I am now on that page you requested, and this is the page that I'm on. As you can see, it says current page 1 because this is page 1, not page 0, because page 0 is the intro screen. I will now show you a little bit of Next-Gen simulator. So it's currently on page 2. I paste in page 0. It does a little intro, flashes some of the lights and opens the windows and closes the windows, and then turns on the stop lights. After it finished that, it sent a thing saying I'm on page 1. Now I'm just going to paste another command in, which turns off the stop lights. And I'm now clicking around the screen where the doors are and the bonnet and trunk is. And when I do that, there is a command going back to the ECU saying, this is what happens. I can then enact on that to say, oops, the door is open, or oops, the trunk is open, and change state accordingly. Next part of the puzzle was the Arduino car. I bought this from Amazon. I think it was about £50. It has a few different functions. It has Bluetooth, it has infrared remote control, it has ultrasonic detection and also line following. I had to modify the code on this so that the lights can be controlled the same as the body ECU, so that when you put the indicators on the capacitor, it would indicate on here. When you put the brake lights on, etc., horn. This also involved modifying the gateway code, because normally the powertrain ECU would not see messages about lights and horn, so they had to be replicated across to that ECU, and that ECU would then send the data across to the little car. The logic for the speed and steering is calculated within the powertrain ECU. It's a function of the accelerator position, brake position, whether the handbrake's on and whether the ignition's on. So there's not much physics in there other than that, but it sort of works. So now onto a demo. What this shows here is when you plug it in, it goes through the introduction sequence. Each one of the then screens will flash through all the different functions it's got, go through the gears, etc., flash the lights, and then come to a resting state. Here I'm now turning the ignition on. I'm now going to turn the parking brake off. If you watch, press it a couple of times. That's because switch bounce. I believe I have fixed that now. What I do is change it to the B mode on the powertrain ECU for Bluetooth. If you saw then when I put the accelerator up and down, the rev counter went up and down. When I put the brake up and down, the brake lights come on. I've now turned the indicators on right, indicators on left, indicators back to the middle, or left again, right again. Now go through the gears, park, reverse, neutral, drive. If you look closely, the steering is on full left-hand lock. Let's open the right-hand window, open the left-hand window. On the body ECU, you should see the window coming down. Now what I'm going to do is lock the left door, lock the right door, switch bounce again, causing issues. That is that video complete, I believe. Now what I'm going to do is show a video of hacking occurring. What I have is an Arduino Nano connected to the chassis CAN bus. It is spoofing the following messages. It's spoofing hazards on, headlight flash, fuel gauge at 40%, coolant temperature maximum, steering at full right lock, and accelerator at 11%. If you look at the screen in the top right hand corner, the chassis ECU and also the body ECU in the middle, you will see these functions playing around. So I've got full left hand lock. I'm now going to inject the messages saying full right hand lock. I'm now flashing the lights and playing with the accelerator. You can also see the temperature going up and down and the fuel gauge changing. Finally, the hazards are on and the lights are on. What you have to do though is interact with it to change the state, so it then reverts it back to its original state of lights off. That's that demo there. Here's another demo with the little Arduino based car. This is Biggie, the mascot for Car Hacking Village in UK. He's now going to drive full left hand lock and I'm going to now send those messages in again for full right hand lock and accelerator at 12%. What will happen is it will stutter because it doesn't know which messages are correct messages. So as you can see, it's fighting back to the right rather than left. Those messages have now stopped. Now he's going to turn around and he's going to go flying off into the sunset. Whee! So final couple of slides. Costs. So these costs are from the mid 2020, not including posting and packing, which have now gone up quite a bit from bits from China. The ECU boards and parts for each of the ECUs are about £50 each, and there are 4 of them. That gives a total of £200. The IO boards and parts for them costs about £25 each. There are only 2 of them for the chassis and powertrain ECU. The body ECU doesn't actually need an IO board, so that's a total of £50. The 3 Next-Gen 3.5-inch displays are £30 each. You can actually use a slightly more basic version for £20, but I thought I was going to use some of the additional functions, but I didn't. That gives a total of £90 for the displays. And then there is the case, the card, the cabling, the switches, the potentiometers, and all those other little bits in the case. That's probably about a total of £160, given a grand total of £500 in old UK currency. Translating that into US dollars at today's exchange rate-ish is about $800. Currently, if you wanted to buy Toyota's version of pasta, it would be $26,780. It has been over $29,000 in the past. However, because I built it for $800, it's potentially a saving of $25,980. So maybe I should have changed this talk's title to Value Pasta Auto, how I built it and saved $25,980. That was my final slide. Here's a thank you slide. I'd like to say thank you again to ASRG for having me today, doing my talk. If you need to contact me, there is my contact details below. If you want to have a look at the Value Pasta GitHub, there is the link for that below. If you want to ask any questions, just get in contact. I am available. Thank you very much and good night.